Here we continue our efforts to describe the time-evolving fluid flows on a rotating planet by way of the Vorticity Equation, which we have just derived by introducing the total time derivatives of the horizontal flows into the geostrophic equations, cross-differentiating and combining. This Vorticity Equation is written as the total time derivative of f plus zeta plus the horizontal divergence times f plus zeta is equal to 0, where zeta represents dv by dx minus du by dy. We'll begin by giving some context to zeta, which is referred to as the relative vorticity, and can be expressed as the curl of the horizontal velocities. Now, picture a column of fluid. Here we are looking at it from above. Imagine it is in a region of horizontal shear, so that there is an y direction gradient to the u velocity and some x direction gradient to the v velocity. The relative vorticity is the combination of these two shears, so that a parcel of water in a sheared flow has the relative vorticity zeta, a function of this shear. This can also be thought of as the spin of the water column. Now, with this in mind, we return to the vorticity equation. This can be dissected to reveal some interesting features. F is a familiar term that we have been calling the Coriolis parameter. In this context, it is also referred to as the planetary vorticity. It is defined exactly how it is under the name Coriolis parameter, simply a function of latitude and Earth's rotation rate. Zeta, which we have just seen, is the relative vorticity, which physically reflects the spin of a water column. The sum of these two gives the absolute vorticity. Now, a change in absolute vorticity is only permissible if there is a finite horizontal divergence, which, when considering the flow as a set of infinitely narrow spinning columns, relates to the vertical stretching and squashing of spinning fluid parcels. This concept of requiring a horizontal divergence to permit a change in absolute vorticity is interesting, and it's one that we should take a step further. Given that we are considering the fluid as vertical spinning columns, the continuity equation of each column can be written as per usual, and we can integrate this over the depth of the fluid h to return the total time derivative of the column depth h plus the horizontal divergence times the depth h is equal to 0. This is saying that in order to change h, the depth of the column, we need a finite horizontal divergence, which is fairly intuitive to understand. Now, this equation has the same form as the vorticity equation, so we can use the common term, the horizontal divergence, to combine these two equations to get this expression. The total time derivative of f plus zeta on h is 0. This term, f plus zeta on h, is defined as q, and we call it the potential vorticity. The potential vorticity is a property of the flow that is conserved along stream paths. For the fluid to change f, its latitude, zeta, its spin, or h, its height, there must be a compensating change in one or both of the other terms. This principle provides a convenient means for predicting the time evolution of the flow.